For the last, 5 or 6 years, the recipe for AI has felt deceptively simple.
Oh, yeah.
If you wanted a smarter model, you just needed more. More data, more chips, bigger clusters. It was a brute force game of feeding the beast every book, every website, everything.
The era of reading everything, effectively.
But looking at the sources for today, it really feels like that era is ending, or at least it's hitting a wall. We are seeing this fundamental shift from the era of reading to the era of, thinking. And it turns out teaching a computer to actually think, to reason through a problem, not just autocomplete a sentence, is a much, much harder engineering problem.
It is. It's the difference between memorizing a textbook and actually passing the exam. For a long time, the way we taught these models to think, specifically the reinforcement learning phase, was basically alchemy.
A dark art.
A total dark art. You'd tweak a parameter, cross your fingers, burn a pile of cash on GPU time, and just hope the model got smarter. But today, we're looking at a landmark study that claims to have finally turned that dark art into a hard science.
We're doing a deep dive into a paper titled The Art of Scaling Reinforcement Learning Compute for LLMs, which we'll just call the ScaleRL study. And this isn't just theory. This is backed by over 400,000 GPU hours of experiments.
Right. And we're also going to look at how this connects to the big players, like OpenAI's O1 and the DeepSeek R1 models.
So the mission for this deep dive is to understand how researchers have cracked the code on reasoning. How do you take a model that knows facts and turn it into one that can plan, correct itself, and solve PhD-level physics problems?
And more importantly, can we predict how smart it will get before we spend millions of dollars training it?
Okay, so I want to start with the why. We have these massive models trained on, trillions of tokens. They can write poetry, they can code, they can summarize meetings. Why wasn't that good enough? Why can't they just reason out of the box?
It comes down to what pre-training actually does. When you train a model on the internet, you're creating what's called a probabilistic world model. The AI just learns patterns. It learns that Paris usually follows capital of France. But that's just association. It doesn't mean the model understands truth. It just understands likelihood.
Right. So that explains the whole hallucination problem. The model gives you an answer to that. It sounds perfect. It's grammatically flawless, but it's just factually nonsense.
Exactly. It's prioritizing sounding right over actually being right. It's mimicking intelligence, not exercising it.
So that's where post-training comes in.
Right. To fix this, we first used supervised fine-tuning, or SFT. That's where humans write out good answers, and the model just copies them. It makes the model polite, helpful.
But it's limited by the human teacher. If I don't know the answer to some complex quantum physics problem, I can't write the example for the model to copy.
You become the bottleneck.
I'm the ceiling.
That is the hard ceiling, and that is where RLVR comes in, reinforcement learning for verifiable reasoning. This is the game changer. Instead of asking a human, does this sound good, we give the model a math problem or a coding challenge. Then we use an objective verifier, like a code compiler or a calculator, to check the answer.
So the feedback loop is no longer subjective. It's totally binary.
The code runs, or it doesn't.
The math is right or it's wrong.
And because the feedback is objective, the model can explore. It can try strategies that humans never taught it. And here's where it gets really interesting. The model started realizing that if they generated longer sequences, if they literally thought for longer, they got higher rewards.
We see this in the chain of thought prompting that's so popular now. But you're saying this isn't just a user trick anymore. The model is internalizing this behavior.
It's becoming part of the model's cognitive architecture. It learns that thinking time creates these emergent aha moments. It might start down a wrong path, stop, realize it's wrong, and then self-correct. That self-correction is what we are trying to scale.
So we know we want them to think. But the ScaleRL paper makes this massive claim that they found the physics of how this learning happens, that it follows a specific curve.
This is the core finding. For years, people just assumed learning was linear. You put in X compute, you get Y smarts, or maybe it was some simple decay. But the ScaleRL team found that RL scaling follows a sigmoidal curve. It's an S-shape.
An S-shape. That implies phases, right? It's not just a straight line up.
Correct. It starts very, very slow. You pour in compute, and for a while, nothing seems to happen. That's the exploration phase. The model is just flailing, trying to figure out what strategy actually gets a reward.
And failing over and over again.
Constantly. If you were watching the metrics during that phase, you'd probably want to kill the project. It looks like a total waste of money.
I'm sure many projects have been killed right there.
I bet. But then you hit the inflection point. This is where their formula comes in. They broke this down into 3 parts: A, B, and C mid.
Okay, let's break those down because this feels like the crystal ball moment.
So A is the asymptote. That's the absolute ceiling of performance. It tells you the best this specific model can ever possibly do with this specific recipe, the hard limit. Then B is the exponent, which is essentially the speed or efficiency of learning how steep the hill is. And then there's C mid. C mid is the scale sensitivity. This is the critical aha moment. It marks the midpoint of that S curve where the rapid improvement just kicks in.
It's like learning a language.
How so?
You spend months memorizing vocab, struggling with grammar. That's the flat bottom of the S. Then suddenly it just clicks. You stop translating in your head and start thinking in the language, and your fluency skyrockets.
That is a perfect analogy. That's the vertical part of the S. The model just devours the logic. And finally, it tapers off as it hits that ceiling, the asymptote.
The part that really struck me was that ceiling. I think there's a common assumption that if you just train a model long enough, it will eventually solve everything.
Yeah.
But this study says that's just not true.
That is the crucial insight. They analyzed all that data, 400,000 GPU hours, and found that different training recipes, different algorithms, they don't just learn at different speeds. They have fundamentally different ceilings.
So some methods will never get past a certain score.
Never. No matter how much compute you throw at them, you could run them for 1,000 years, and they still won't solve the hardest problem.
You can't just brute force your way out of a bad algorithm. It's like trying to win a Formula One race with a Honda Civic. No matter how perfectly you drive, you are physically limited by the engine.
Exactly. And the beauty of this math is the prediction. You can run a small experiment, say for a couple thousand GPU hours, fit this sigmoid curve to the data, and then predict exactly where the model will be at 100 times the scale.
That changes the economics completely. You don't have to build the whole skyscraper to know if the foundation is cracked.
Right.
But to get those results, they had to fight what I'm calling the algorithm wars. The paper goes deep into the battle between PPO, GRPO, and their new solution, CISPO.
Yeah, this is where we get into the plumbing of intelligence. So PPO, proximal policy optimization, was the old standard. It's stable, but it's heavy. It requires a critic model, which is a second neural network that critiques the main one. That eats up a ton of memory. It's expensive.
Okay, so DeepSeek came along with GRPO.
Right. GRPO group relative policy optimization was a brilliant move for efficiency. It got rid of the critic entirely. Instead, it generates a group of answers for the same prompt, say 6 different attempts, and compares them against each other. The best one in the group sets the standard.
Which sounds great. Efficient, fast. But they found a fatal flaw in it, what they called the fork token problem. This seems really specific, but why does it matter so much?
So imagine a model reasoning its way through a problem. Most of the time, it's just following a standard path, but every now and then it generates a token like wait or however or let me recheck.
The moment the model decides to change direction, the fork in the road.
Yes, that's the fork token. It signals a pivot in the logic. The problem is, statistically, these tokens are incredibly rare, and standard algorithms like GRPO use something called clipping to keep the training stable.
Right, to prevent it from overreacting to one weird data point.
Exactly. But because these fork tokens are so rare, GRPO sees them as statistical outliers, as noise, and it clips them out. It ignores them.
That's ironic. The algorithm is literally suppressing the aha moments because they look like errors.
It's optimizing for the average safe path and discarding the brilliant rare pivot. And that's why GRPO struggles with really deep reasoning.
So how does CISPO fix this?
CISPO stands for Clipped Importance Sampling Policy Optimization. Instead of clipping the token probabilities directly, which effectively silences the token, it clips the importance sampling weights.
Okay, let's unpack that. How does changing what you clip make a difference?
It's subtle but critical. Think of it this way. GRPO mutes the token. CISPO, on the other hand, lets the token speak, but it puts a governor on how much that one token can change the model's entire worldview overnight.
So it still hears the signal.
It captures the signal. We need to pivot without letting the system crash. It allows the model to learn from those rare, high-impact tokens. The result in the study was a 2x speed-up and, more importantly, a significantly higher performance ceiling. The model just gets smarter.
The math is beautiful, but you have to actually run it. We're talking 100,000 GPU hours. The engineering section reads like a horror story of everything that can go wrong. They built this system called PipelineRL.
You have to understand the scale. In traditional RL, there's this stop-and-go traffic. The generator makes text, then stops, then waits for the trainer. The trainer does math, then stops, waits for more text.
And all that idle time costs a fortune.
So PipelineRL is about keeping the pedal to the metal. It splits the brain. You have a pool of generators and a pool of trainers running asynchronously. But the real breakthrough is what they call in-flight updates.
Sounds like mid-air refueling.
That's a perfect analogy. The generators never stop working. The trainers send updated weights over the network while the generators are still producing text. They update their brains on the fly without hitting pause. It makes the whole process about twice as fast.
But then they hit the butterfly effect. They found that tiny numerical errors were breaking the whole thing.
Oh, this is the nightmare of every ML engineer. It's the FP32 precision fix. See, in these huge systems, you have inference kernels running generation and training kernels doing the math. People often use lower precision math to speed things up.
Like rounding off decimal points.
Right. But they found that tiny discrepancies, at the 6th or 7th decimal place, were causing the math to go haywire.
And what does that look like on the graph?
A flat line, reward plateaus. The model just stops learning. You are burning electricity, but the intelligence isn't increasing because of a rounding error. They had to force the system to use high-precision math just to stabilize it.
It really shows how fragile this thinking process is. It's not just code, it's sensitive physics.
Yeah.
Speaking of which, let's talk about the data. The outline mentions something called zero-variance filtering.
This is one of those efficiency hacks that separates the pros from the amateurs. When you're training, you generate a batch of answers for a prompt. Let's say you generate 8 answers.
Okay.
If the model gets 0 out of 8 correct, what does that teach it? Well, in this setup, almost nothing. The gradient is flat. The model is too dumb for that problem right now.
And if it gets 8 out of 8 correct,
It already knows the answer. It's busy work, a waste of compute.
so they just throw those out.
Exactly, that's zero variance filtering. They automatically drop any prompts where all the answers are failures or all are successes. They only want to train on problems in the Goldilocks zone, where the model gets maybe 2 or 3 out of 8 right.
That's the zone of learning, where you're stretched but not broken.
Precisely. And this connects to the mirrored J-shaped distribution they talk about. A standard data set has a J-shape where most problems are easy. For RL, you want the mirror image. You want a data set where most problems are just barely too hard.
And this is dynamic.
Yes, dynamic dropping. As the model gets smarter, problems that used to be hard become easy. So the system sees the pass rate hit 90% and just kicks the prompt out of the data set. The model is constantly being forced to graduate to harder material.
Relentless. So we have the mouse, the algorithm, the machine, and the data strategy. What was the result? The paper compared a model called Scout to a standard dense model. And this felt like a headline moment to me.
This is arguably the most important finding for the industry. They compared Scout, a 17 billion parameter mixture of experts model, against a traditional 8 billion parameter dense model.
So a bigger, more complex architecture.
Right. But here's the kicker. Scout, using the specialized training, reached the 8B model's peak performance using only 1/6 of the compute.
Wait, 1/6? That's not an optimization. That's a different ballgame.
It completely upends the scaling laws we've believed for 5 years. It proves that architecture plus methodology can beat raw size. You don't just need a bigger brain. You need a brain structured to learn efficiently. We are moving from how big is your cluster to how good is your training physics.
And that efficiency lets you just let the model think longer.
That's the other knob they can turn. They found that increasing the generation length, say from 14,000 tokens to 32,000 tokens of thinking space, is a ceiling-raising strategy. It makes the model capable of solving problems it literally couldn't solve before.
It's not just retrieving information, it's synthesizing a solution. We're seeing this in the real world now, right? With OpenAI's O1 doing PhD biology and DeepCoder 14b using a sandbox to actually run code.
DeepCoder is a great example. It writes code, compiles it, runs it. If the code fails, negative feedback. If it runs, reward. It's learning from objective reality. And there was a fascinating side effect. Learning to code made the models better at everything else.
The transfer learning effect.
Yeah. Right. It turns out that coding requires such structured, rigorous logic that when a model gets good at it, that skill transfers to math, to logic puzzles, to general reasoning. Teaching AI to code is basically teaching it how to think logically.
Makes sense. You can't bullshit a compiler. You have to be precise.
Exactly.
So bringing this all together, it feels like we're standing at a threshold. We've moved from the dark arts of random tweaking to a principled, predictable science.
We have. We know the curve, the sigmoid, we know the parameters. We have algorithms like CISPO that preserve those flash of insight moments. And we have the infrastructure to run it all at a massive scale.
But it seems like the bottleneck is shifting again. It's no longer about, do we have enough data? We have the internet. It's not, do we have enough chips? It feels like the new constraint is patience.
That's the big picture here. The integration of all these methods is creating what we call agentic models. These aren't just chatbots waiting for you to type. These are systems that can plan, verify, and correct themselves over long horizons.
They're not just regurgitating the past.
No. And here is a thought to leave you with. We are now building systems that don't just learn from what humans have written, which is finite and full of our own biases, but from the objective reality of what works.
Because the verifiers don't lie.
Right. So if models can now verify their own logic, and if we know that giving them more time to think raises their intelligence ceiling, are we approaching a point where the limit on AI intelligence isn't data or even electricity, but simply our human patience to let the model sit there and think for an hour before it answers?
That is both exciting and a little terrifying. The idea that the answer to some huge problem might be sitting inside the model if we just wait for the thinking bar to finish loading.
It's a brave new world of physics.
It certainly is. We'll be watching those sigmoid curves closely. Thanks for listening to this deep dive into the physics of AI reasoning. We'll see you on the next one.